Very good morning students. In today's class we are going to start with module 3 where you are going to have design of finite impulse response filters. As you know there are two types of filters, digital filters which are IAR filters and FIR filters. IAR filters are infinite impulse response filter where the response will be infinite, whereas FIR filters are finite impulse response filter where you will be getting a finite response. So let us design this FIR filter and try to implement it with the help of various structures. So here we are going to start with structures for FIR systems. So we'll be drawing the structure of an finite impulse response filter where the first structure is direct form 1 structure, cascade structure, linear phase structure and lattice structure. So these are the four structures you are going to learn here. So the first structure, as I told, it is direct form 1 structure. So how will you draw this direct form 1 structure? So let us write down what is the transfer function of this FIR filter. As you know, a causal FIR filter, it is characterized by its transfer function h of z, which is given by h of z is equal to summation n is equal to 0 to n minus 1 bz z power of minus m, and h of z can be written as y of z divided by x of z, where the summation m is equal to 0 to n minus 1 bm z power of minus m. So now let us cross multiply this x of z to the right hand part. So we will be getting y of z is equal to summation m is equal to 0 to n minus 1 bm z power of minus m into x of z. Now in order to get the output equation, let us convert this z domain into time domain equation. So for that let us take inverse z transform for the above equation. So if you take inverse z transform for the above equation, we'll get y of n is equal to summation m is equal to 0 to n minus 1 bm. So inverse z transform of z power of minus m into x of z will be x of n minus m. So this particular equation, it is the output equation which is just a weighted sum of the present and the past input values, and it does not depend on the previous output values. And this you can well understand by this equation. Y of n is equal to summation m is equal to 0 to n minus 1 bm x of n minus m. So if I am going to expand this particular equation, I will be getting as b naught, by substituting different values of m, you will be getting as b naught x of n minus 0 plus b1 x of n minus 1 plus b2 x of n minus 2 plus b3 x of n minus 3, plus it will go on till n minus 1. So using this equation, if you observe, y of n will be sum of the present input, that is x of n, and past inputs x of n minus 1, n minus 2, n minus 3, along with the weightages b0, b1, b2 and b3 and go on. And also you can observe it does not depend on the previous output. So directly we are writing y of n is equal to. So using this particular equation, we are going to draw direct form 1 realization. So below the structure shows the direct form 1 realization of the FIR filter. So how to draw this structure is, first you need to write what is the input and output. So first let us write in the left hand side x of n, and in the right hand side down corner I am going to write y of n. So in between whatever the structure I am going to build, it is the structure of FIR filter using direct form 1. So this structure we are going to write with respect to this output equation. As I told, this output equation, it is sum of the weighted sum of present and past inputs. So we'll start with x of n multiplied with b naught, which will be given to a summation point, plus, and this x of n I am going to give it to a delay element. So delay element if you give, you will be getting as x of n minus 1. So which will be multiplied with b1, and it is given to the summation block down. So again in the next part, so this x of n minus 1 will be fed as an input. So output will be x of n minus 2. Parallelly we will be multiplying with b2, then it is added to the previous outputs. Like this we will keep on adding till m is equal to n minus 1. At the end, if you add all this weightages along with the present and the past inputs, you will be getting y of n. So this structure will call it as direct form 1 realization. So let us solve a problem and try to understand how to draw the structure. So this is a problem statement where, this is the problem. Realize an FIR filter. So we have to realize the FIR filter structure. With impulse response, h of n is given as h of n is equal to 1 by n power of n, u of n minus u of n minus 4 using direct form 1 structure. So here if you want to draw the FIR filter using direct form 1 structure, you should know what is the output equation. So as discussed, you should have this equation y of n is equal to summation m is equal to 0 to n minus 1 bm x of n minus m, right? So here the problem statement they are given h of n. So this h of n you have to convert as y of n. So how to do this? So let us solve it. So the solution is, first take down what is the given h of n. So it is 1 by 2 power of n u of n minus u of n minus 4. So let us draw this h of n first. So u of n minus u of n minus 4 will be 1 from n is equal to 0 to n is equal to 3. Remaining all, it is going to be 0. Then I need to multiply with 1 by 2 power of that corresponding value of n. So if I substitute different values of n as n is equal to 0, 1, 2, 3, I will be getting a graph which is shown there. So this is my h of n. So for this h of n, let me represent in terms of impulse responses and its delay. So h of n I can write it as, at n is equal to 0 the amplitude is 1. So this can be represented as 1 into delta of n. And n is equal to 1, it is 1 by 2. So I can write it as 1 by 2 delta of n minus 1 plus 1 by 4 delta of n minus 2 plus 1 by 8 delta of n minus 3. So this h of n we have represented as sum of the unit impulse responses with delay. So now let me take Z transform of this above equation. So if you take Z transform of the above, h of n Z transform will be h of z, and Z transform of delta of n is 1, and Z transform of delta of n minus 1 is z power of minus 1, and 1 by 2 is a constant. So it is 1 by 2 z power of minus 1 plus 1 by 4 z power of minus 2 plus 1 by 8 z power of minus 3. So as the next step, this h of z I can represent as the output by input. So it is y of z divided by x of z is equal to the same right hand side equation. Next, what I am going to do is, as I need only y of z, x of z is taken to the right hand part and it is multiplied with each and every term. So let us take inverse Z transform of this above equation so that you will be getting the output part y of n. So take inverse Z transform. So if you take inverse Z transform for the above equation, the inverse Z transform of y of z will be y of n, and inverse Z transform of x of z will be x of n, and 1 by 2 z power of minus 1 x of z whose inverse transform will be x of n minus 1 plus 1 by 4 x of n minus 2 plus 1 by 8 x of n minus 3. So this is my output equation, and this equation if you observe, it is of the form summation m is equal to 0 to n minus 1 x of n minus m, whereas m it is ranging from 0 to 3. So from this equation you will be able to draw the direct form 1 realization. So how to draw the direct form 1 realization is, start with the input x of n and the output y of n. So in between we are going to have the direct form 1 structure. So as we have seen here in the model, so we are having m is equal to 0 to 3. So we will have b0, b1, b2 and b3. Right. So there are 3 delay blocks needed. So from x of n we will give it to a delay block so that you will be getting x of n minus 1. Again that will be given as an input for the next delay block z power of minus 1. So the output will be x of n minus 2. Again this x of n minus 2, it will be fed as an input for the next delay block. The output will be x of n minus 3. So first let us generate all the delay elements starting from x of n minus 1, n minus 2 and n minus 3. So now parallelly let us multiply with b0, b1, b2 and b3. Whereas b0 is equal to 1 and b1 is 1 by 2 and b2 is 1 by 4 and b3 is 1 by 8. Then we'll use the summers adders in order to add each and every term. So first we'll be adding x of n with 1 by 2 x of n minus 1. Then again it is given to the another summation block, so that we'll add further 1 by 4 x of n minus 2. Again another summation block to get 1 by 8 to add 1 by 8 x of n minus 3. So the final output, if you observe, it is the sum of x of n plus 1 by 2 x of n minus 1 plus 1 by 4 x of n minus 2 plus 1 by 8 x of n minus 3. So which is nothing but the output y of n. So this complete structure represents direct form 1 realization of FIR filter. Okay, this is about the realization of FIR filter using direct form 1 realization.